this semester was types of data. And that's important to us because we know there's only certain kinds of analyses that are appropriate for certain kinds of data. For instance, when we're dealing with categorical data, we're typically organizing that by frequency. In other words, hair color is a categorical or nominal data variable. Okay, and we wouldn't be thinking of the kind of numerical analysis we do with a numerical variable like mean or standard deviation and stuff like that for hair color. We think more about counting the frequency. How many people were brunettes? How many people were blondes? How many people had red hair? And perhaps displaying that graphically with a bar chart, as opposed to numerical data where we're looking at something that will summarize where the middle of the numbers are, like median and mean, something that gives us an idea of the spread of the numbers, like the standard deviation or range, or the quartiles, and for numerical variables, and so on and so forth. So basically, we're dealing with 3 or 4 types of variables. SPSS really kind of pares it down to 3 types. Okay, sometimes we bring up another couple of types. For instance, categorical. Well, that's nominal. I think they call that nominal in SPSS. Numbers or continuous scale can be called a continuous variable, numerical variable. I think in SPSS they call it a scalar variable. A lot of words, a lot of names for the same thing. Now, sometimes people distinguish between integer type data, like say, for instance, number of siblings in a family, where the number would be 1 or 3 or 4 or something like that, and call that discrete numerical. In other words, a simple count. Now, even though you're generally going to handle the data probably the same way because it's still a numerical variable. In fact, SPSS doesn't even distinguish between discrete and scalar variables. It just lumps them together. Now, on the other hand, if we're going to be talking about the average number of siblings in the Bronx, in Queens, and so on and so forth, and that might be a number like 3.47 and 2.13 or 1.4, right? Then that moving average, that's really no longer a discrete variable, that's a numerical variable. But the original data might be discrete numerical. So let's go through this and see what we can do with this stuff. Okay, question number 1. Let's see, I got already went past it. Did it print properly? I might actually have to open this up. A researcher records for each participant in the clinical trial. This is not displaying properly. It doesn't like to create PDFs very well. I'm going to go right back to the actual quiz itself so we can actually see this a little bit more clearly. Okay. Okay, a researcher records, let me see if I can't blow this up a bit. Yeah, oh, a second. Well, no, that's not going to work. I have to keep it wide. A researcher records for each participant. Let me just make sure that you guys can still hear and see me. Could you just type in the chat box? Okay, good. Thank you. Yeah, I had a little bit of a Java error that you might have noticed before when I was loading that page, so I wanted to make sure things were still working. Researcher records for each participant in the clinical trial the amount of alcohol they consumed per month and their cholesterol levels. Indicate whether each variable is categorical or quantitative. Okay, so we got the amount of alcohol they consume per month and their cholesterol levels. So what do you guys think that might be? Okay, I got a couple of opinions there. Okay. Okay, let me just see what's happening there. Yeah, Greg, I can make you guys the presenter if you have something that you want to display on your screen or something like that. Like maybe if you want to show us a process where you're working on SPSS when we get to that thing. Oh, you hit the wrong button. Okay. No, but however, I can turn your mics on and off individually. So if you want to ask a question, if it's too long a question to type in, you can always do it. You can always get me to turn your mic on, and you can speak into the mic. Okay, so what do we think there? I would say probably, yeah. Well, cholesterol. Why would cholesterol would be categorical if it were high, low, medium, good cholesterol, bad cholesterol? That would be categorical. But if it's a number like cholesterol level of 180 or 100 and 200 or 225, it's going to be numerical. So in this case, I would say alcohol is quantitative and the cholesterol level is quantitative. Now, cholesterol level could be quantitative, could be categorical if you were just putting it into categories: high, low, good, high, or something like that. Okay, let's take a look at the next one. Good. Okay, a researcher records for each participant in a clinical trial their race or ethnicity, and the severity level of their depression symptoms. That's usually, let's say that might be like a scale, like 1 to 10 or something like that. Indicate whether each variable is categorical or quantitative. Okay, so let's see, what do we have here? We got race and ethnicity, right? Well, that sure does sound like categories, right? So let's eliminate the first choice, and let's eliminate the third choice. So we're left with these two. So severity of depression symptoms, categorical or quantitative? Okay, well, what do you think we might be choosing there? Okay, anybody have an opinion on that? If I don't, I'm not going to kill too much time waiting for answers and stuff like that. Categorical, it depends on how it's presented. If you're using, occasionally, you might be using a categorical scale. Like this is a tough question because the answer implies that you know a little bit about how typically you would describe depressive symptoms. Like for instance, if I asked on a scale of 1 to 10 how much pain you were in, then that would really be a special kind of numerical variable, wouldn't it be? It would be yeah, for low, medium, high, it would be categorical. So the right answer, if a low, medium, high, the right answer would be the second one. But if we're putting it on a numerical scale and asking them to assign a number to it, a relative number to it, then it would be quantitative. Okay, it would be quantitative, would be numerical or quantitative, but in that case, it would be ordinal. In other words, the numbers have some order. Yeah, I'm not. In fact, I hate this question. Right? That's kind of, In fact, if you look at the answer sheet, Professor Wyka goes into a little bit of an explanation of why it's in this case she's choosing quantitative as the right answer, right? And the reason is because the way that this is typically described, they use a scale kind of like that a patient might assign to a level of pain, for instance, like 0 to 10 or something like that. Okay. All right. So, yeah, some of this stuff, there's always, whenever we do this every semester, there's some debate over at least one of the questions on variables, even though you would think it'd be the easiest thing for everybody kind of agree on. It often isn't. An examination of medical records of 10,000 women showed that those who were short and fair skinned had a higher risk of osteoporosis had a higher risk of osteoporosis. So, an examination of 10,000 women showed those who were short and fair skinned had a higher risk of osteoporosis. Well, would this be prospective or would it be retrospective? Is it looking into the history of these women or is it looking forward? So, yeah, I agree with Greg, right? I agree with Greg that it's a retrospective study because we're looking back into their medical histories, right? Now, if this had been a study like the Framingham study, you guys ever hear of the Framingham study? It's where they took tens of thousands of doctors and they followed them over the course of several decades to track their risk of heart attack. And they kept track of their cholesterol levels, smoking status, so on and so forth, other health status. And they were actually following them to see which of them developed heart disease, which of them didn't develop heart disease. And that's kind of one of the classic studies where they kind of assigned a lot of the risk factors for cardiovascular disease. So that would have been a prospective study. This is a retrospective study. Which of the following is a reason to use randomization? To balance the groups on variables known to affect the response, to eliminate possible researcher bias, to balance the groups on possible confounding variables. That kind of like sounds similar to this first one, right? These two sound almost like they're saying the same thing. And gee, yeah, you know, that might be nice. We don't want all the smokers. If we're studying the risk of cancer from asbestos, we don't want all the smokers in one group and none of the smokers in the other group, because that is possibly a confounding variable. So both this one and this one seem to be saying that. Eliminate possible researcher bias. Yeah, you want to know something? Well, you know, when the researcher is selecting who goes into which group, he may unconsciously bias the research by putting healthier people in one group and less healthy people in another group. So certainly I wouldn't say, you know, it looks like more than one answer here is correct. I certainly wouldn't say none of these. So I think probably the correct answer is probably all of these, right? Do we all agree on that? I'm not looking at the answer sheet, so you guys are going to have to help me a little bit. Okay, good. Cespedes, the Cespedes study. Now, this is one that we looked at in class. I think this was one of the reading materials. And let me just see if I got a note on that, like what that was. Cespedes study can best be described as experimental, observational, or none of these. You guys happen to remember that? I wonder if I can. You know, I'm gonna answer that question first, and it's an experimental study. My recollection of it was literally that you took people and put them into two groups, and you evaluated the performance of the two groups. So that's an experimental study. An observational study is one where you might be watching the if prospective, you might be watching the development of disease in several groups, two groups or several groups, but you're not actually altering the environment for the two of them. Like an experimental study might be taking someone and putting them on a placebo or a drug, or something like that, and seeing how their blood pressure measurements change, or putting one on a diet, on another not on a diet, or perhaps some sort of intervention where you might say, well, how do patients, how do psychiatric patients perform if the nursing staff gets behavioral training, behavioral science training, compared to how do the patients, what's the condition of patients if the staff doesn't get that kind of training. So it's testing. Instead of testing a chemical, you're testing whether an intervention has some effect. So yeah, experimental study sounds exactly what it sounds like, is when you set up groups and you compare the two groups and so on. Okay, so experimental study. If we get a chance, I'll see if I can't find that paper. Austin et al. Study can best be characterized as, now again, if you have an observational study, it's one in which you are making observations, not making not making an intervention, not altering the conditions for the two groups. Okay, and SPSS variables. Now, this is something that you would have to know from SPSS, of course, but you guys know that when you open, unfortunately don't have SPSS on this machine. That's a whole area of contention right now in terms of what the licensing on SPSS for us. But I'm not, as an instructor, I'm not eligible for your discount. So, and the school only has like an on-site license right now. They try and save a few bucks, I guess. In SPSS, the variables are typically recorded. Remember, there's two views we have: the data view and the variable view. Most of the time, when you start up, thank you, Madeline. When you start up, you're in the data view, and you can flip back and forth between them. So, in the data view, the main view, the variables are in columns. Like the first column might be the patient number, second column might be or some sort of ID. Second column might be age, gender, weight, all in columns. Now, when you click on that variable view, right, then the then each variable is in the rows. But that's usually not where you're actually looking at the data, because all you can see in the variable view, you can see how the data is structured, but not the data itself. In the data view, which looks like a spreadsheet, well, in that section, the variables are in the columns. Okay, in SPSS, the cases are typically recorded in, well, one's the columns, the other one's going to be the rows. So each individual case, literally each individual measurement, each individual person, patient, subject, and so on and so forth. Each row would represent a subject. So for instance, if you have a study with 500 subjects, you would have 500 rows. If you have a study with 10 variables, you would have 10 columns. Crude rates are preferred over age-adjusted rates for comparisons between different population groups or trends over time. Is that going to be true or false? And I think this is a good time for us to maybe get into discussing what we mean by age adjustment. Maybe we can do an example of age adjustment. By the way, if you look at the answer sheets on Blackboard that are behind us, I think that it will give you an idea of what it'll give you pictures, at least, of the SPSS variables. Maybe that part actually worked. Let me just open that up. Did it work? Could you see it? No. No, unfortunately not. Yes, it doesn't like to print out stuff from the quizzes. Okay, it's just not designed for that. Okay, so what about these crude and age-adjusted rates? Well, in this case, crude rates are not preferred over age-adjusted rates. And we'll talk about what crude rates are and what age-adjusted rates. In fact, maybe we'll do a calculation just in case that there's one on the test. Age-adjusted rates, if you have a population, if you're comparing two groups, say we're comparing Canadians, let's say that we're comparing people in Alaska to people in Florida in terms of lung cancer rates. Well, people in Alaska tend to be a lot younger than people in Florida. Florida's a big retirement community. You're going to get a lot of older people. Older people have higher rates of lung cancer. So now you say to yourself, well, what's the rate of lung cancer in Alaska? And it comes out to be, say, 100 people per year per 100,000. And the rate in Florida is 300 per 100,000 population. You say to yourself, well, gee, Florida has 3 times the rate of lung cancer that Alaska does. Well, just in terms of the actual numbers of cases, that may be true. Let me just make sure everybody's muted here. That may be true just in terms of the number of actual cases, but there's nothing going on in Florida, nothing in the environment in Florida that's causing those extra cases. It's just simply that the population in Florida is much older, generally much older than the population in Atlanta. So we need a mechanism for saying, let's take those crude rates, that 100 per 100,000 or the 300 per 100,000, and let's even out. Let's get that age. Let's get the difference in the age distribution of the population out of that calculation, so that we aren't biasing this based on the age of the differences in the age distribution of the two populations. And I'm gonna do an actual. I'm gonna actually. Since that's the last question on here, and I think somebody actually asked about number 10, I'm going to actually do a calculation here that does that on age adjustment. Let me see if I can't find one now. Age adjustment, and I'm going to start with an Excel file if I can. Okay. See if I can get one that has just raw data. Okay, here's one that just has raw data. I'm going to, let's see, age-specific rates. I'm actually going to eliminate some stuff here so that we can actually do this from scratch. And I'm going to clear all of this. And I'm going to clear all of this. This may come out a little bit more complicated than a problem on the test might be. but it's good. You'll get to see a lot of calculations here, and hopefully you'll have the, like, it'll be here for you to go back and review later on. So you can go, if I go through it a little bit fast for you, you can always go back and do it a little bit slower. Okay, so I'm ready. Okay, so now here we have the population of New York during some period of time. I don't know exactly when, and we're looking at the number of deaths due to crude female mortality rates due to heart disease or by cardiac. Actually, I think any kind of cardiovascular disease probably is really what it is. Okay, so we know from the annual mortality and morbidity reports in New York City that in this particular year, there were a total, this is a total number of female deaths due to heart disease in New York City, was 12,650. Okay, and that includes all of these different age groups. As it happens, they list the age ranges and the number of deaths in the mortality and morbidity results. Okay, so if I wanted the crude mortality rate due to heart disease, it's going to be equal to 12,000 women out of the 4 million population in New York City. So the rate or your probability of know her age, if you randomly pick a woman out without selecting her based on age, would be 0.003 during the course of this year. That's really kind of it's a good number. It describes what the risk is, right? It's less than 1%. It's 1/3 of 1%. It describes the risk for a randomly chosen woman, but it's not really very easy number to work with. So I'm going to take that number, right? And I'm going to say to myself, let's take that number, right? And I'm going to multiply that number by 100,000. And now that tells me the number of women that will die per 100,000 of population. Okay, so the risk of dying from heart disease for women in New York City is 300 per 100,000 population. Okay, get it there. I could have actually done this right here in the formula, which was the total number of total mortality divided by the total female population. I could have just put that times 100,000 up there, so it would have been per 100,000 population overall. But you could also just do it here with a second step. Everybody okay with that? Not like a earth-shaking calculation or anything like that. I'm going to do exactly the same thing here for male mortality in New York City. This, by the way, it's old data. It might be from 10 or 15 years ago, but it's actually real data from the mortality and morbidity report. Equals, let's see, the sum, oops, escape. Let me click into here, equals sum, parentheses, total number of male deaths is 9,000. There's fewer number of deaths, but probably there's fewer males there too. So let's see what the male mortality rate is going to be equal to. It's going to be equal to 9,900 men over 3,700,000. It's going to be 0.002. And if I want it per 100,000, I'm going to take this number and multiply it by 100,000. Okay, and so the rate at which males die in this population is 262, almost 263 per 100,000. Well, all our lives we've been told that men tend to die, have much higher risk of cardiovascular disease. If you're a man and you're 40 in your 40s or 50s or something like that, and you have chest pains, right? They're all over you in the emergency room. A lot of women don't get diagnosed when they have appropriately when they have chest pains because the perception is that men are more at risk. In fact, they really are more at risk. But what's happening here is that if you look at this, what's the percentage of women in each one of these age groups in this population? Well, I'm gonna do that here. The percentage of women that are under 25 in this population is equal to 1 million women out of 4 million women. So 32% of the women in this population are under 25 years old. Depressing, right? For those of us that are older. But that's a whole other issue. Now, I'm going to copy this down, but I think I mentioned to you guys, you don't have to worry about this too much because you could actually do the formula for each one of these cells by hand if you wanted to, but I'm going to save myself a little bit of time by putting a $ in front of the B11. So when I copy it down, it calculates the average for each one of these. It does the calculation for each one of them without changing the total for the population. Okay, I'm going to drag the corner down. And there we go. 32% are in the 24 to 44 age range, so on and so forth. 2% of the population is over 85. 11% of the population is over retirement age, is 65 to 84. Let's do the same thing for males. Equals this number divided by the total number of males, which is 36%, even higher percentage, right? That's interesting. So I'm going to put a $ in front of here and a $ in front of here. Okay, and I'm going to click on this, drag it down. Whoops, let me undo that. Okay, I'm going to click on this and drag it down to here. And let's take a look at what we wind up with. You know, if I look at this, 11% of the population of females, 11 and 2 really, 11 and 2 point something, that's almost 12, and 2 is 14% of the population is over 65 for females. But males, gee, it's 8.5, and 1, 0.09, 0.009 would be 1. Only about 9 or 10% of the population is over 65 for males. So there's a lot more older women in the population than there are older men in this population. So the population of women tends to skew older than the population of men. Let's see how that affects the death rate for these women. Okay, so the death rate per 100,000 is going to be equal to the number of deaths in that age group times 100,000. I'm going to multiply it by 100,000. Actually, I'm not even going to bother for now. Divided by the number of women in that group. Okay, so very low. Look, it's like a tiny death rate for women in that age group. It's going to be the same for men, but in this particular case, it's going to be interesting. So let's do this, and it looks like the death rate for women that are 45 to 64 is less than 1%. It's only about 1% for women in this age group, but look, it's 7% in this group. So let's see what it looks like for men. Okay, let's see the death rate in each one of these groups, 11 out of this number, right? And then copy it down for each different age group. And the bottom one's the overall, which is the, oops, what did I forget to do there? I made a mistake here. Let me do this again. 11 divided by that one. Okay, again, also a very small number. See, now I could use fill down. I'm just grabbing it by the corner there so that it copies the formula down. You may have seen me do that before. I could also just click in here, drag down, and say either fill down, right? And on Excel and on the PC, you probably find that same thing on the right-hand side over here. On the Mac, it's on the left-hand side. Or you could just go up here to edit and say fill down. Any one of those three ways just gives you the same answer. So let's see what the rate of the death rate is for these different. Look how much higher the death rate is for the oldest portion of the population from cardiovascular disease. Those people that are 85 and older is almost 8%. That, right? It's a very high death rate, right? So 8% of the population is dying each year from heart disease in that age range over 85. So since the population of females has so many more women that are over 85, 87,000 versus only 2,600 in this particular study are over 85. Yeah, I bet you that's changed a lot in the last few years as medical as heart disease prevention has progressed and cancer cures have progressed. I'll bet you that these numbers are quite a bit different. Might be interesting to do that one of these days. These crude rates may not reflect accurately what's going on here with these populations, because we're applying the rates of disease, the death rates, to two different populations. We remember the way that we got the crude rate was we calculated the number of deaths just based on that population, which is older, and this population, which is generally a younger population, right? So, but we could see the individual death rates are not really all that different, aren't they? 7%, let's see, 85 and older, 7% for female, and 7% for males in that age range. It's just that there are so many more females in that age range. They're contributing to all those deaths. Okay, so now let's do an age adjustment here. And the way that we're going to do the age adjustment is I'm going to copy this column here. I'm going to copy it down here. Okay, so now I am now going to, now I got that, and then I'm going to say to myself, you know, I'm going to not compare, I'm going to take these two death rates for all of these different age groups. I'm going to take this one, okay, and I'm going to paste it down here. This is for death rates for females, rated deaths for females. I'm going to say edit. I'm going to do something special. I'm going to say paste. I'm going to say just paste the values themselves. I don't need the formula. I just want to paste. I don't want to mess things up. And because it's actually, if I expand this format cells, if I add a few decimal places, okay, maybe even another one, it'll be a little easier to see this. Okay, so this is the female age specific death rate. Okay, is in there. Okay, so now I haven't put the population in here yet. I got a reason for that. And over here, I'm going to put the male age specific death rate. And they're not going to be all that different. So here's the male age specific death rate. I'm going to do the same thing here. I'm going to say edit, paste special, just copy the formulas down there, rather the values. And okay, that one came up with, yeah, because in this column it came up with, it was expanded already. And now what I'm going to do is I'm going to say to myself, instead of comparing these two death rates for all the age-specific death rates to two different populations, in other words, applying the female death rate to the female population and the male death rate to the male population, I'm going to apply them both to the same population. I could choose apply them both to the male population, female population. I could choose apply them both to the female population. Or, you know what I'm going to do in this case, just for the hell of it? I'm going to say apply it to the female plus the male population. Okay, so now these numbers represent the total population of New York City in each one of these different groups, total male and female populations, right? And now, instead of applying the two different I could have also applied them to anything I wanted to, as long as it was the same population I was applying, no longer different populations, but the same populations. Okay, I could have applied them to the population of Florida, population of Alaska, right? Anything I wanted to, or maybe even the U.S. population, overall U.S. population. To me, it made sense. Just add the two populations together and just apply them to the total population for the city. Let's see how many people would die. If they're dying at that rate, this rate, what females are dying at this rate, and there's that many of them, how many females would die? It's going to be equal to the death rate times the population size. Okay, so we'd have 46 deaths there. So I'm going to copy this down. Fill down. Okay, and that's how many females would die if their population were distributed this way. How many men would die if their population is distributed the same way? Well, it's going to be equal to the rate at which men dies times the population in that age group. Okay, and I'm going to do the same thing here. I'm going to fill that down. Edit, fill down. Okay, so if it's applied to the same population, how many would be dying now? Equals how many women would be dying? Well, the sum is that many. How many men would be dying? And the sum is, okay, that. So let's see what the total population is. Total population of New York at that time was, okay, just about 8 million. Okay, so what's their death rate for females in this population? Well, death rate is equal to, it's equal to 19,000 divided by 8 million. Okay, it's 0.002, or in other words, we could also do it this way. It's this number times 100,000. It's 244 women per 100,000 would die during the course of this year. Well, let's do the same thing for men. Equals this number divided by number of deaths divided by the total population, right? And that's the rate of death. Okay, now what about, how is it per, let me change that to the same units. It's going to be this number times 100,000. And it comes out to be 336. So now we see that males indeed do die at a higher rate than females. The crude data suggested women died at a higher rate than males do, but in fact we have just shown that that difference in that rate is really due to the fact that the population of women in New York is older than the population of men. The distribution of ages, it is older for women than for men. So that is, I'll cover that in a sec. That is why that question 10, when it asked, if you know, sometimes when sound drops out, usually it's an internet issue more than anything else, either on my end or your end. It's impossible for us to tell, really. So if you're patient, it probably usually comes back. But yeah, you should by all means alert me right away if you lose the picture or if you don't hear my voice. So at any rate, that's the idea here is that this is really a better measure of who really dies at a higher rate from heart disease. Men, in fact, are at greater risk for heart disease. It looked like women were at greater risk here only because their population is older, and older people tend to be the ones. No, don't worry about sorry. Like I said, I'd rather hear that if you have problems with communications, I'd rather know about it rather than just go stumble on and not realize that I had left you guys behind. Okay, so that's why that question 10, that answer for question 10 is false. That most of the time, the age-adjusted rates are preferable to the crude rates if you want to make a real evaluation of which population is more at risk. Okay, let's move on to, so we got a chance to get in a quick age adjustment calculation here, which I think is really good because if it comes up on the exam, maybe that'll help out. But like I went through it kind of a bit more quickly than I would have preferred. But on the other hand, you guys, if you want, you can always go back to this recording and play it again. Okay, so let's go on to quiz 2. Materials, let's see, quizzes. And I'm going to play it back from here because it doesn't really print out all that well. Oh, we got the answers down here. Okay, good. Quiz 2, I'm going to say continue. Okay, let's get it to load. Okay, question 1. Following histogram depicts the heights of 50 men and 50 women. Okay, which of the following best describes the shape of the distribution? Okay, let's see. Okay, this is the heights of, now in this particular population, it's, you don't have any tall women and you don't have any short men. So it's kind of a weird population, right? Okay, and this isn't, first glance, when I first looked at this, my impression was this is two different histograms, right? They just happened to put it on the same, in the same image here. But in fact, it's one histogram, 62 inches, 64, 66, 68, 70. The way this is distributed, well, actually, you don't know. They're not males and females. Some of these could be males, some of these could be females. All we know is that we had 10 people that were 64 inches tall. We had 8 people that were 65 inches tall. We had nobody that was 67, and so on and so forth. We don't know which are males and which are females. Yeah, you guys got ahead of me, right? It's bimodal. And you would expect it to be bimodal, wouldn't you? Because we would expect one peak for females, who tend to be shorter, and one peak for males, who tend to be taller. It might not be this dramatic with this nice separation right in here, but you would really, that would not be unusual. If I really did it in real life, this is probably the way I would expect it to look. Let me just see if I can't get this onto here. Okay, in real life, might be a bit less dramatic. It might be something like, right, something like that, right? Almost a normal distribution, but definitely something, something that would suggest that there's two groups buried into that population. One is a group of females, one's a group of males, and there's two different peaks there, which might be the average or median for females and the average for median for males. But you're right, exactly right. It's bimodal. Okay, a nurse measured blood pressure of each person who visited her clinic, following as a relative frequency histogram for the systolic blood pressure readings for those people aged 25 to 40. Blood pressure readings were given to the nearest whole number. Okay, so let's see what we have here. So we have, let's see, relative frequency. Now keep in mind where this histogram counted, we had frequency here, which means that the height of each of these represents the actual number of people, actual number of subjects or patients that were in that group, or students, whatever these happen to be. And so, for instance, this tallest peak represents 11 people who, in this sample, who were 71 inches tall. If I asked you how many people were over 71 or over inches tall, it would be 11 plus 5, 16, plus 2, plus 3 rather, which looks like 19 people. This one's a bit different. This one, each bar represents the relative frequency. In other words, the percentage. Okay, so relative frequency here is 15. Thank you very much, Isabel. The relative frequency is 15% in this group between 100 and 110. And the most frequent outcomes were between 110 and 120, the systolic blood pressure. 35% of the people were in that group, and so on and so on and so forth. Right? So if you add it up, 15%, 35%, 25%, 15%, 10%, 5%, well, you've added all these up, should add up to 100%. It's represented as percentages. Now, if it's 100 people, this would represent 15 people. If it's 200 people, the 15% would represent 30 people. But we're looking at it a little bit differently. We're looking at it as percentages, relative frequency, rather than the actual frequency here. So let's keep that in mind as we answer this question. Approximately what percentage of people aged 25 to 40 had a systolic blood pressure of at least 110, but less than 120? Okay, well, here's 110, at least 110, but less than 120. Well, that's only that one bar in there, isn't it? Right? So I would say that that's probably 35% would be the right answer there. Oops, sorry, 35% would be the right answer there. Don't let them fool you. Thank you, Greg. Right on. Okay, so a nurse measured the blood pressure of each person who visited her clinic. Blah, blah, blah. Okay, the blood pressure given. Now, what's this question now? Oh, they just repeated the drawing. Approximately what percentage of people aged 25 to 40 has systolic blood pressure less than 120? Well, less than 120 means only these two bars to the left. So we've got 35%, 15%. So that's half of the population, right? 50%. Okay, if I make a mistake here, guys, feel free to point it out. Why are the ages listed as percentages? I guess only because there might be a few reasons for doing this. Let's say that this would represent a study that was 100,000 people, right? If we're 100,000 people, 35%, this would be 100,000 people. This would be 35,000 people. This bar would represent 35,000 people. This bar would represent 5% would only be 5,000 people. So the scale here, the way that you would have to draw this would be kind of awkward, wouldn't it? Because the numbers, it's easier to display these numbers if you show them relatively than in any other way. Also, it makes it generalizes a little bit, right, into something that's more of a description of a general population rather than the specific sample that you're looking at here. right? So I get, this, it's just another way to display it. Okay, you take away the actual numbers here, but you maintain the relative. That's why I call it relative frequency. You maintain the relative relationship. Like this one is 7 times what this one is, right? 35 versus 5. It's 5%, 7 times what that one is. Where you'll see people do this a lot. Sometimes you see them do it with a logarithmic scale. You ever notice that stock tables, the stock graphs, very frequently logarithmic scale? It's because, the Dow Jones average now is 16,000. But 30 years ago, the Dow Jones average might have been only 1,000. So to show that big a range, they make the scale logarithmic, which compresses it, so that instead of having to have like the height of 7 pages of paper to show the relative difference between what it is now and the 16, instead of having to, like having to display it across 4 pieces of paper, they can compress the scale down to a much smaller area. So, and also it makes it in some cases a little easier to interpret in some ways. Nurse, okay, you got the same thing there. Given that 200 people were aged, approximately how many had a systolic blood pressure less than 130? Well, it's just literally the kind of thing that we're just doing there. Systolic blood pressure less than 130. Okay, so that's everybody from this point to the left. Well, I'm going to do something little slick here. Since it looks like it's going to be easier, I'm just going to see how many people are to the right. So we have 15%, we had 10%, that's 25, and 5 is 30% of the population is greater than 130. That means 70% had to be less than 130. And since the population is 200, 70% of 200 is 140 people. I got that wrong. Let's see, did I get the 15 and 10 is 25, 30%, 70% is below this, less than 130, 70% is below this, 200 people, 70%, that's 140. Is it? Yeah, I guess it's 150, except that's 75% of the population. Is it me, or am I right? 35 plus 35 equals 50. 35 plus 15 is 50, plus that's 7. Oh, it doesn't add up to 100%. Is it me? Am I right? Doesn't add up to 100%, does it? 15 and 35 is 50%, 75%, 85, 90%. Oh, I got that wrong. 50%, 75%, 75. Tell me I'm wrong here. 75, 80, 90%. It adds up to 105%. Well, excuse me. You think that's what it is? You think that's halfway? You could be right. You could be right. Okay, in which case I probably won't want to do that since it's so hard to read. I think you're probably right. I'm just misreading that. It's kind of like, you're probably right. Well, maybe it's looked like 8% and 3%, maybe 8% and something else. But yeah, maybe that's just a little under 10, and this is just, around 3 or something like that. You're right. Okay. Yeah, I don't like that. It's confusing. All right. So yeah, but we would have put the same answer down anyway, right? Because it's so close. I mean, there would literally there'd be no other answer that would be even close. So we would have got the right answer anyway, doing it either way. So you should have been able to just say, oh, it's easier to count these and subtract from them. That was my point. My point is that it might be easier to just count the percentage of people that are above 130, subtract it from 100%, and then just multiply it by the 200 for the population, right? So either way would work. Just kind of like I just assumed those things were a little bit cleaner than they were. The proportion of adults aged 15 to 49 who are living with HIV/AIDS is 0.5% in Latin America, 1% Caribbean, in Eastern Europe, Central Asia, 0.6%. Suppose we include the proportion for Sub-Saharan Africa, 5%, to this data set and calculate the standard deviation. Would you expect it to be significantly larger, smaller, or remain the same as the standard deviation of the proportions without the observation for Sub-Saharan Africa? Well, what is standard deviation a measure of? Standard deviation is a measure of variability or spread, right? Well, if we look at the sample we had before, 0.5%, 1%, 0.9%, they're clustered pretty. There isn't a lot of variability. They're very close together. And now we throw in this number that's really almost an outlier, a much bigger number. So it's going to make the variability, and that includes the range, that includes the variance, that includes the standard deviation. So we would expect all of them to be significantly larger. Right? Okay, good. So you guys agree. I see we got some people agreeing with me. A distribution that has the right tail longer than the left is considered skewed, not skewed. I'm going to draw that one because that brings up an interesting point, because I want to talk about what that means when we say skewed. Okay, whoops. Okay, I got that back. Let's talk about skewed. Okay, so now here is, I'm going to do my best to draw this here with this silly thing. Here's my best estimate of a perfectly drawn normal distribution. So one of the properties of this is that the ends are asymptotic, that it's symmetrical. This side is a mirror image of this side. 50% of the population is below the mean, and 50% of the population is above the mean. The other thing is that the mean is equal to the median, right? So if the average is the same number, in a perfect normal distribution, the average and the middle number are the same thing. In other words, if this were blood pressure and the mean were 100, the median, the middle value, would be 102. Okay, so now let's take a look at what happens if you take this distribution, and instead of it being a perfectly normal distribution, the tail on the right extends out this way, right? So what do we have? We have a bunch of people in here, right? And what are those people doing to the median? Well, they're not affecting the median all that much because there aren't a lot of them. It's a skinny little tail, but they are affecting the mean. So what's happening is the median is staying here, but the mean is moving over in this direction because these values are pulling the average up. So if it's pulling the average away from the mean, the mean away from the median in this direction, it's called positively or right skewed. If it were tail, if there were some values down here, like very small values, that were pulling the mean, the average, away from the median in this direction, that would be negatively or left skewed. This is positively or right skewed, right? So let's go back to that question. Okay, good. I'm glad to hear that. Let's go back to that question and see how we would answer. Distribution has the right a tail longer than the left tail. Okay, right tail longer than the left tail. It's skewed, right? It's not symmetric. It's skewed, but it's skewed to the right because there's people in that tail with very high numbers. Very fat if it's weight, very high blood pressure if it's blood pressure, and so on and so forth, that are pulling the mean away from the median to the right. So that's skewed to the right. The mean is skewed to the right. Had they been really skinny and they were way down at the had extra people down at the left hand side, then it would have been skewed to the left or negatively skewed. Okay, good. I'm glad to hear that. Okay, so a recent survey poll of male Mexican American adolescents to determine their association between smoking and unhealthy behaviors. Below is the data. Each boy aged 10 to 18 was classified according to smoking status and his response to a question asking whether or not he liked to do risky things. Okay, so let's see, smokers and non-smokers. So this is an example of a crosstab, a cross-tabulation, or also sometimes called a contingency table. So most of the time, you like to put the exposure or the risk in the rows and the outcome in the columns. In this case, we ask them, do you smoke or not smoke? Well, if you're a smoker, you're a non-smoker, you're in one of these two rows. And then in the columns, we put down whether that person says he likes doing risky things, or he doesn't like doing risky things. So in this case, it looks like we had about a couple of hundred, maybe about 300 people that they interviewed, Mexican American adolescents that they interviewed, and 45 of them happened to be smokers and like doing risky things. 36 smokers didn't like to do risky things. Now, among the non-smokers, 46 like doing risky things, 153. So there were a lot more people, a lot more that were non-smokers, right? The total number of non-smokers is 46 and 153, which is 199. And the total number of smokers was 45 and 36, which is 91, I guess, right? Something like that, 91. Okay, so now with this table, you're right. Thanks. I love when you get ahead of me. It's encouraging because I know then that you're following me. Okay. What proportion of sample smokers likes risky things? Well, there's 91 smokers, right? So the proportion would be 81. Is it 81? You're right. It's 81. I'm wrong. The proportion that like to do risky things is 45 over 81, which is a bit more than 50%, maybe 55% or something like that. What's the proportion of sampled non-smokers that likes to do risky things? Well, that's only 46 out of 153. So in one case, we have, I'm making this number up. I didn't do the actual calculation, but you can see it's as Greg mentioned, it's 45 over 81. And the proportion of non-smokers that like to do risky things is 46 over 153, which is roughly about a third, or about 0.53. Okay, so there's our answer to decimals, except that you want to put a couple of extra. Notice it asks you, everybody keeps asking me, oh, how many decimal places should I extend this to? Well, in this case, they actually tell you they want 4 significant digits, right? So these are not the right answers. I just did it quickly. 46 over 199. Okay, so there we go. Actually, 25, more like 25%, right? This would be more like 25. Whatever the real answer is, it's in the answer sheet, so I wouldn't, I don't want to dwell on this too much. Using the NC 800 data set, not North Carolina birth data set, we called it 800 because we trimmed it down to 800 cases. It was really like 35,000 or something like that. Data set, answer the following questions. And in order to do this, you had to actually do this calculation in SPSS. So you had to calculate what the average mother's age is in this group, what the percentage of mothers in the samples were married, and what was the most common race and ethnicity that was for this group. Well, let's see what we have here. The average mother's age, and that's a numerical variable, right? So that we would calculate a descriptive variable we would be interested in is the mean or the average. And that would be the mean or average of the mother's age. I think the variable name is M age in this data set. The percentage of mothers in the sample that were married or not married, that's a categorical or nominal variable. So that you would be interested in a frequency, right? So if you had 200 women and 100 of them were married, then the percentage of women that were married would be 50%. So you would actually calculate that using SPSS. I think on the answer sheet, they actually have the charts and tables coming from SPSS. And between now and Saturday, I'm going to see if I can actually maybe record that separately on a machine that has SPSS actually working on it. But for this, we would use, right, the sequence that we would use for getting to this when we have the data set open in SPSS would be to go up to Analyze, right? We go up to the top to Analyze, click on Analyze, swing over to, and since we're not breaking this up into different groups, we just go to Analyze, Descriptive Statistics, and then choose Descriptives. And tell it, make sure it's just checked off that one of the things you want to count in options, checked off that the average is what you want to calculate. Okay, and then we would choose the variable M age, mother's age, and move that from the list of variables boxes into the box that has the variables you want to work with. Say OK and OK, and you would get a box that gives you a variety of statistics, including the one you need here, which is the average. Now, as far as the percentage of mothers in the sample, that's a numerical variable. We would want a frequency there. That's how we would calculate that. And there we would tend to analyze, go over to descriptive statistics. The next thing we choose is descriptive statistics. And then instead of choosing descriptives, or the next thing is explore, we would just go straight across to the top one, which is frequencies, and tell it that we want to know the marital status, whatever that variable is. Move that variable into the analysis box, say OK, and then it will give you the number of women that are married, number of women that are not married in this population, and the percentages, right? So that would do that for you. You would use analyze, descriptive statistics, analyze. And the most common ethnicity, well, in that case, we want to take the ethnicity variable, analyze, descriptive statistics, frequencies, and choose, instead of choosing how many women, the marital status variable, we would choose the ethnicity variable and ask it to count them and give us the percentages of them. And it would be again, analyze descriptive statistics frequencies, because it's a numerical variable and we want to know the frequencies. I would say that you should assume that you might get a question on SPSS. The tables are in the answer sheet for this session, but I'm going to see if I can't get to a machine between now and Saturday where I can record myself answering this question, so you can actually see me do it. But you remember the sequence, right? You go up there to analyze, and you should be able to get through it pretty well. Okay, what was the median mother's age? Okay, here's another one that would involve SPSS. The nice thing about this is that you save all the work of doing the calculations. It's doing all the work for you, or all the heavy lifting at least. What was the median age for the mothers who smoked during pregnancy, for mothers who didn't smoke during pregnancy? Very interesting. Now this one, if I go to analyze descriptive statistics, right, there's a numerical variable because we want to know the middle age, M age, same as we found the mean for in the previous problem. This time we want the median. So we would go to analyze descriptive statistics, except this time, instead of choosing descriptives, which we normally would do if we wanted to just find the average age for all the mothers in this study, we're going to go to, instead of descriptive statistics, we're going to go to explore. Now, when you go to explore, it gives you the opportunity to select two variables. One is the main variable, which is the mother's age, because you want the median of that. And the other one is a factor variable. And the factor variable is groups that you want to break it up into. So we go to analyze descriptive statistics, explore, and move the MH variable into the dependence box, the big box on top, and then move the smoking status, which is a categorical variable, which could be smoked or didn't smoke, 1 or 2 in the data, right? And move that into the factor box. And now it will analyze this for the median age as if there are two different groups, one smoking group, one non-smoking group. The only problem is that you should make a note of, or remember, or make sure you code whether or not what the number value is for smoked or not smoked. Like if 0 represents smoker and 1 represents non-smoker, or if 1 represents smoker and 2 represents, you should make note of that because it's going to ask you which two numbers to use, right? So you'll be able to put in, oh, well, the factors are 0 and 1. So you can let it know what that is. And you can go ahead and do that, and you'll find that you'll get one median for mothers who smoked and another median for mothers who didn't smoke. Yeah, I could do that on Saturday. Either that, or I can do something. Separately on a machine with SPSS. Let's see if I can't find, copy SPSS somewhere on some machine that I can work with, or do it separately, and so you have a demo of it. Answering this question, because I suspect whatever you might wind up getting is going to be similar to this anyway. Okay, all right. And the last question is: were there any outliers in the mother's age in either the smoking or let's see, any outliers? Inspect side-by-side box plots. Well, one of the things that you're going to discover that as you do these analyses, analyze descriptive statistics, if you go into descriptives or if you go into explore, right, it will automatically produce some graphics for you. In the options, you can choose what those graphics are. You could say for numerical variables, You could tell it you want a stem and leaf. Nobody uses that anymore, really. A histogram. You can have also box plots. And in fact, what it will actually do is it will create, for instance, analyze descriptive statistics, explore for mothers who smoked during pregnancy. It will actually give you box plots for the distribution of the mother's age. And when you do that, you can see what the ranges of these box plots are. And Saturday, I'm going to go over box plots so that you guys understand what the feather on the bottom, on top, and the stars, and so on and so forth, what they all represent. And in fact, SPSS will highlight for you which values are outliers by displaying them as little circles or boxes, little circles or stars outside of the range of the box plot. So you would simply easily be able to open that that file, that chart, box plot that it presents, and see, oh, smoking status group didn't have any outliers, but the non-smokers did have outliers, or vice versa. Let me just before we finish up here, I'm gonna stop at this point now. We've been going on for a while. Let me just go and open I think, do I have it? No, actually, I should do it again. Like it doesn't display well when you try to export it as a PDF file. I'm going to do it in here. And if I go over here, the answers, that should be this one, I think. Okay, let's open it up. Okay, here we go. Okay, let's get these SPSS. Let me zoom in on this. Okay, skewed to the right. Okay, they're skewed to the right. Okay, let's see, fill in the blanks. Okay, here's the moving, like from descriptives to analyze descriptive to descriptives. You can bring these answer sheets with you, just so you remember like what the sequence is with these things. And here, let's take a look at our box plots. Here's the frequency table. Again, this was analyze descriptive statistics frequencies. I've been doing this too long if I actually remember this stuff without having to look at the software. But at any rate, that's unfortunate for me. So at any rate, mother's age and smoke. So remember the mother's age is a factor list. Now it will ask you to label the cases by ask you to put in the numbers, like in other words, smokers 1 and 0. You don't see that here, but it will ask you. It'll come up with a little box and ask you to put in those numbers, and you'll have to tell it what those numbers are. And let's see. And here's the box plots. And look, I don't see any outliers here, right? We were seeing the outliers up here and up here, and so on and so forth. We've seen them as circles or squares or something like that. I can see that the median. Let me just do this while we have this open. What do we have here? This is the range of rages for mothers who did not smoke. You had mothers from 15 years old to about 42 years old, right? That's the overall range. These two feathers represent the overall range. The dark line in the middle represents the median, the middle value, the 50th percentile or middle value, the middle person. The middle person's age was about 27 or 28. And this bottom line here represents the 25th percentile. 25% of the women were below 22, and 75% were above. And this represents the 75th percentile. The median is the 50th percentile. Half were below this level, half were above. Top part of this box is the what they call the third quartile, or the 75th percentile. That's 32%. That age 32. 75% of the women were under 32, and 25% were over 32. And the interquartile range, that's the range between the 25th percentile and the 75th percentile. In other words, the middle 50% of the women. And that is the interquartile range is from 22 to 33 or something like that. Okay, so that's what that represents. And this group over here represents the women who are smokers. The average age for women who smoked is younger than the average age for women who, the median, middle age for women who smoked is different than the middle range, is lower than the middle value or the 50th percentile. for women who didn't smoke. The other thing is that, see this over here? The median looks like it's pretty close to the middle, doesn't it? That suggests that this distribution, if I looked at it as a histogram, looks like it's pretty symmetrical. This one, the median is squished towards the bottom, which suggests that there's that the age range is wider, like the right tail tends to stretch out a bit, right? So it might look something like this with that right tail stretched out. This looks like it's right skewed, like the mean is above the median. Here it looks like the mean and the median could likely be pretty similar. But here it looks like there's going to be a dramatic difference between the average and the median here. So this looks like it's right skewed. This looks more symmetrical. It's not perfect. This is a little bit, there are a few women that are a bit older, than you would say, not quite enough to be outliers, but that are a little bit older than you would expect. If we're completely symmetrical, it might have stopped there. But it's pretty close, right? Where this one is clearly not even close to being symmetrical, right? The median is pushed way down to a younger age. So there's older women. There's less than you would expect. There's more older women. There's older ages than you would expect for this to be symmetrical, right? You would expect it to end over here. Okay, so I hope that's at least an introduction to this, and we can pick up on Saturday and talk about, Saturday we're going to talk about diagnostic tests in addition to like maybe doing some of the SPSS. We got diagnostic tests and we got probability